Okay guys, so this is the second part of the introductory videos about vectors, and where we left off was we had talked about writing a vector A in terms of its components AX and AY. But in order to make this make more sense, we should look at different math things that we can do with vectors. And so the first thing that we can do is we can actually add vectors. And adding vectors is not like adding scalars. For example, if I have a displacement of 4 miles north and a displacement of 3 miles east, I think everyone can figure out pretty easily that the displacement, my total displacement, is 5 miles at some angle that I can calculate because the tangent of that angle is opposite over adjacent. Okay, so I think that's like 37 degrees for a 3, 4, 5. But in any case, I think we can all agree that if I add 4 miles and 3 miles in this case, I don't get 7. Okay, 7 miles would be the distance that I've traveled, but we know that that's not a vector, that's a scalar. The vector would be 5 miles. That would be my displacement. Okay, so there's a special term for when we add vectors like this, and what we're actually doing is a math thing called adding vectors head to tail, and this falls under the general heading of a geometric method. So there's two of them, head to tail, and so for this every vector has a tail and a head. So the head is the arrow, the tail is the other part. And when we add vectors head to tail, what we do is, okay, let's say I have 4 miles, okay, that's a vector with a tail and a head, and let's say I have another vector which is 3 miles which has a tail and a head. So what I do is I take the tail of the next vector, okay, and that attaches to the head of the previous. So what I mean by that is, let me go ahead and grab this. I'm going to drag it so that its tail touches the head of the first one. Okay? So let me show you that one more time. Alright, this vector has a tail right here and a head right here, and so I drag it so that the tail of one touches the head of the other. Okay? And then what you do is you draw the resultant. That's what we call the sum of two or more vectors from the first tail to the last head. And in this case, this is the first tail and this is the last head. So that's the resultant. And we already talked about how that was 5 miles at a 37-degree angle. Again, magnitude and direction. Okay, and the great thing about doing head to tail is that if you have multiple vectors that you want to add, like for example, let's say that I went 4 miles north and then I went 3 miles west and then I went 4 miles southeast, and then I went another 4 miles, oh maybe that's more, maybe that's 5 miles southwest. Okay, so all of these vectors can be added using head to tail, and I'm just going to drag the vectors themselves, so I'll go tail of that goes to the head, okay, and the tail of that goes to the head, and then the tail of that goes to the head. And then if I want to find the resultant, do this in a different color, I'll start at the first tail and I'll go to the last head. Now I would need some sort of a grid or something in order to calculate how much that was and at what angle. Okay, so this is a graphical method, and it's somewhat helpful. But if we want to know exact, we need to do something else. Before we talk about that, though, the second geometrical method is called the parallelogram rule. Okay, now the distinction I want to make between these two methods, the parallelogram rule is really only good for two vectors. Head to tail, on the other hand, is good for multiple vectors. Okay, and the parallelogram rule says, okay, again, let's say I have 4 miles going north and 3 miles going east. Okay, so in parallelogram, what I do is I form an angle with the two vectors. So in other words, they're going to act like rays. So they're going to be like rays. So instead of putting them head to tail, I put them so that their tails are together. And that goes kind of sort of like this. See the difference? Now I have an angle. Okay? So I'm going to form my angle. Okay? And then I'm going to construct parallels to my two vectors. So I need something which is parallel to the one going north, kind of like this. And I need something which is parallel to the one going east, kind of like that. And then my last step is to draw the diagonal, or the resultant, which is a diagonal, from that vertex to the opposite side. So what I mean by this is I start at the vertex right here and I go to the opposite side, and that is my resultant. Okay, now the parallelogram rule is actually more powerful if you have two vectors that are at some sort of an angle like this. So I've already put them together. Okay? Maybe they're two ropes tugging on the same object, and we want to know the total effect. So again, I have to do two parallels, and this is the hard part, is drawing them parallel. Sometimes I'll take a ruler and slide them over. I can even copy and paste, but I'll start at the vertex and I'll go to the other diagonal. So that's what we mean by the parallelogram rule. Okay, so these two geometrical ways of adding vectors can also be used to subtract vectors, but we'll get to that in a moment. But they're not very good at telling us any numbers. In order to figure out the actual numbers, we need an algebraic method. And really the best algebraic method that we have is using components. So we talked about doing components earlier, where a vector A has a component AX and AY. And now it should make sense to you why I've drawn the arrows as I did. Because if I take vector AX and I add vector AY to it, I'm going to get vector A. This is a very different way of writing addition. Normally we would think, oh, that's 3 plus 4 equals 7. But when I add vectors, then I'm talking about head to tail. And you can see that the tail of AY touches the head of AX, and the hypotenuse, the resultant, the vector A, goes from the first tail to the last head. So that's kind of where that comes from. Alright, now back to components. Okay, let's say I want to add two vectors. Okay, here's vector A, which has components AX and AY, and then I have a vector B, and vector B has components, let's make that AY, so it has components of BX and BY. Okay, so let me outline the general strategy, and then we'll put in some numbers. So this video might go a little bit beyond 10 minutes, but you'll deal with it. Okay, so the general strategy for adding components is basically you have to calculate the components of each vector. Okay? So if you have 5 vectors, you're going to have 5 x components and 5 y components. If you only have 2 vectors, you only have 2 components. But you do that using sine or cosine or even tangent. Okay? And again, look back at the SOHCAHTOA video for instruction on that. Then you add the components. So what I mean by this is you add up all of the x components and you add up all of the y components. And usually what I suggest is to organize this in a table. And again, an example will make more sense. Then the last step is to take, and we'll call these subtotals that you come up with in step 2. Take the subtotals and construct a right triangle with them. And then that's going to give you your resultant. Okay, now that doesn't make any sense unless we put some numbers on it. Okay, and just for fun, I'm going to use some numbers that are fairly straightforward. Okay, so vector A is going to be 6, and this is going to be 40 degrees, and vector B is going to be 10, and this is going to be 20 degrees. Okay, so this should be pretty easy. If you have issues with what I'm about to do, you need to go back and look at SOHCAHTOA. Okay, so AX is going to be A cosine 40. Okay, AY is going to be A sine of 40, and A is 6, by the way. Okay, BX is equal to B cosine of 20, and BY is equal to B sine of 20. And so in this case, we're going to have, we'll call that 4.6, and this one will be 3.9. The next one's going to be 9.4, and this last one is going to be 3.4. Okay, so that's step 1, is finding the components. Okay, step 2 is to add them up, and I like to organize them in a table. So what I do is I write it kind of like this. So here's vector A, here's vector B, x component, y component. Now if you have more than 2 vectors, you can just keep on going. Okay, so if there is a vector C, a vector D, so on and so forth. Okay, and we'll see how to do that a bit later on, but this is going to be our subtotals. Okay, so AX is 4.6, AY is, 3.9, BX is 9.4, and BY is 3.4. So you can just see that where I'm putting things. Now, you have to be careful, because what if B was going this way? So it was 9.4 this way, but 3.4 down. In that case, the y component would be negative. Okay? So you have to keep in mind the direction, and usually we say that this is our positive. Okay? So I add these up, I'm going to get 7.3, and for this one I'm going to get 14.0, and those are my subtotals. Okay? All of the x components added up give me 14, and all of the y components give me 7.3. So my last step is to take the subtotals and make a right triangle with them. Okay? Sorry, it looks like construct art. So construct a right triangle with them. So x is 14.0. Notice how I make that a vector. Okay? So you could call that, this would be Rx for the resultant in the x direction. And this could be Ry, or 7.3. Okay, so then the resultant is the hypotenuse. Okay, and we just do a little bit of math here. So 7.3 squared plus 14 squared. Pythagorean theorem, we take the square root of that, and we get 15.8. Okay, and then to find this angle, the tangent of that angle is y over x, so that means that the angle is the inverse tangent of that, and that gets us about 27.5 degrees. So that's our angle, and this r is our resultant. So it's 15.8 in whatever units we have at 27.5 degrees. Okay, so that's a little bit long, but that's how we add vectors using the component method. So I suggest trying this on some of the homework problems.